So we're going to take a quick look at contour diagrams, contour maps. If you're a hiker, you may be familiar with this, and the lines indicating elevation. So this is a technique we can use to turn a two-dimensional piece of paper, map, screen, into something that can communicate 3 dimensions. So our first step here is looking at what a topographical map is. They have things called contour lines. That's what a contour graph diagram is about. And each contour line on a contour map represents elevation. So, and usually they have to understand them, they have to give a little number of what each one represents. So they're usually equally spaced. And so let's look at some examples. And they're usually in terms of the flat plane is XY, and Z is the elevation that's going up. That's the only way to do it, but that's generally how they're done. So we could see here, this is communicating that this would be at, say, 500 feet. We don't know the units for sure, but and then 400 feet and 300. So it's going down as we go further away. So there must be, now this would be, since there's no top or anything, this would indicate sort of a flat top mountain. Everything up here is 500 feet. And then we go down to 4, 3, and so forth. This contour is communicating that the highest parts are here. So here's 800 feet, here's 800 feet on this side, so 2 taller peaks. And between them, you know, we come down 700 on this side. This side's a little steeper, actually. You've got to remember, it's the smaller number. There's a 200-foot change in elevation between this one and only 100 foot here. So this side is steeper. That's what that communicates. We get down to 500 feet here and down to 3, so it's kind of a saddle pass between 2 mountains higher here. So this would, if you were traveling, this would be the better way to go instead of having to go all the way up to 800 feet or, you know, this steep path here. So kind of, if you're reading the map, if you have to go through here, you go through here. Okay. This would show a long valley. So notice this side is both the left and the right far sides are 200, and then 100 down here. So it's kind of going down. And then there are the possibilities of impossible things. So you can't be 100 feet and 200 feet at the same time. So this one makes absolutely no sense. This one here, sorry, I didn't have this. Okay, so this would communicate kind of a U shape down like that, and a mountain, so forth. And so your activities are going to be to look at some graphs and then match them to their contours. And again, so thinking of the XY plane as being our two-dimensional reporter of things, this shape here would project downward to the contour map here, contour diagram. Okay, and so we would see 110. This is the highest point here. Not necessarily flattened out, but it maybe not enough to put another contour in there. We know this is 110, say, feet up, 100 feet, 90, 80, and so forth. And we see as they get closer together, since they're going by tens, these would be steeper. The ones that are further apart are less steep. Okay, and so then how do we use contour maps and contour information? Well, we can use them with equations. So we're going to see there's this equation, x squared plus y squared is equal to some constant, and that gives us a, as we looked at before, sort of a parabolic cone going up. And so this contour would, we would choose intervals. Here they're going up every 2, so the first 2 would be up here, so that's 2 up in the Z direction would be a circle, and then we go 2 more up. And each time we go 2 up, actually, notice they're getting closer together. And as you see, it is getting steeper. That's what that means. It's changing by 2 faster. Okay. So as we get the pattern, this is 2, 4, 6, 8. So this would be 10, 12, and so forth. Okay. And then we've got our X and Y on the bottom. So let's look at an example, and then we'll be pretty good to go. Okay. So, and this was the one we had, there was a project on this, but I figured we got the problem, so we're going to not worry about the project. So how do we use this diagram? Okay, so you're in a room 30 feet long with a heater at one end. In the morning is 65 degrees. So here's our heater. In feet, here's the room. Here's the heater, and then 30 feet away is the other side of the room. So depending upon where you are, you could be up to 30 feet away from the heater. Over time, the heater will bring the temperature, as we see, up to 85, and then when it's supposed to kick off. So, but notice it brings 85 to a certain, and then it kicks off. But if you're further away than that, you might not actually be 85 degrees, so the far wall doesn't get as warm. Anyway, how warm will it be 10 feet from the heater in 10 minutes? Well, 10 feet, 10 minutes, that would be right here. Now the contour line is saying just below that is 75, right? We're a little bit above that, so we could estimate it to be about a degree, maybe 76 degrees, because we're going from 75 to 80, and I would say that looks like about 76. Okay, and you'll see in the solutions that's about what they do. Now you could try to be a little bit more accurate, I guess, and try to call this, but this is 5, 6, 7, it could be 8. So I'm going to call that, that would be 8 feet. Let's see if we can, how accurate we can get. So at 8 feet away, we're 75 degrees. And then at, what is this? This is going to be about 18 feet. We're going to be 80 degrees. So it's a 5 degree difference, 10 degree, wait a minute, what am I doing? 10 minutes. These are not feet, these are minutes. So if I say I'm at 8 to 80, 8 to 80, right? That's 5. That's about 10. That is 5 divided by 10. That's about a half a degree per. And so, okay, that makes sense. Per minute. And since we're not 8 minutes, we're 10 minutes, 1 whole degree. Okay, so 76 makes sense. So let's try this. How about 15 minutes after it was turned on? How warm is it? 10 feet from the heater, 15 minutes after it was turned on. So here's 15 minutes. There's 10. There it is right there. Now we've got to say, okay, we could kind of do the same thing. 75 down here, 75 at 8 minutes, 80 at 18 minutes. So it's a difference of 5 degrees. We're now at going from 8 to 18, right? So we're at 15. 15 is how many minutes more than 8? 15 minus 8 is going to be 7 minutes. So we multiply that by a half, and that's about 3.5. So if we take our 75 plus 3.5, we get to about 78.5. They want you to round it to the nearest degree, and if we sort of just eyeball it, it's probably going to be closer to 78 than to 79 would be a little bit closer. So we'll call it 78 degrees. Okay, and again, all we can really do is do a fairly good estimate on these ones. So give those 3 problems a try in the homework, and I'll have 12.4 for you ready for you next. Thanks. So now, what does a linear function look like in 3 dimensions? So in just 2 dimensions, a line is a skinny thing with no width, right? It's just length. So in a 3 dimensions, it's going to be missing one of the dimensions. So it's going to have length and width. It's going to be a plane, but it's going to be a flat plane. There's not, this is not a line. A line in 3 dimensions is a plane. So let's take a look at what that gives us as far as an equation. So in general, what we have is we have a slope in an x direction that we're going to label as m, right? And then we're going to have another slope, could be the same, but doesn't have to be, in the y direction. Okay, so we have 2 slopes multiplied, and so you see sort of the point slope formula here in 2 dimensions, and then there's a constant that gives us the z for some particular point, and then the variable of z is equal to that. So it's the sort of, I guess, we would say the z-intercept, right? 2 of the slopes, and there we go. So you can get this graph to go. So you've got your intercept here, because if x and y are both 0, this goes away, and that would be your z-intercept when x and y are 0. Okay, so we can look at this in either way. We can look at it in this form when we have z equals. You could also move z over, have it equal to c. So let's take a look at what that means for coming up with an equation. So we've got 3 points. The plane, that's a linear equation in 2 dimensions. Remember, what we're looking for is basically z equals z naught plus the slope in the x direction, x minus x naught, plus the slope in the y direction, x minus y, y minus y naught. Okay, so to find the slope in the x direction, or the y, actually, what we do is we find a point where the x's don't change, and what that's going to give us is how z is changing in relation to y, because x is not changing. And so we see this point and this point. Okay, so what I'm going to do to find the slope, I'm going to line them up. This is my Vedic math system from ancient India, about 3,000 years ago. They like to do things vertically and crosswise. So here we line it up. We notice that the x's are the same, so we end up with 0. So this is going to be our slope in the, it's actually slope in the y direction, because x is not changing, y is. Remember, this middle one here is the y, and this is the z. So we subtract. So 0 minus -1 is +1. And then we get 1, subtract 3, that's going to give us a -2. Take the y, tuck it underneath the z, and that gives us a slope of -2 in the y direction. So this is our n. To find the slope in the x direction, what we need is 2 points where the y's are the same. The y's are not changing. And so we'll use this one, 0, 1, 0, 1, and 3, 0, negative 1. Okay, line them up over each other. We subtract one from the other. It doesn't matter really which one you want to put on top. You'll see you'll get the same values. 1 subtract 3 is going to give us negative 2. 1 minus minus 2, so that's 1 plus 1, which is 2. Remember, this is our z, this is our x. It's going to give us the slope in the x direction. The change of x, the change in z over the change of x. And we take this x and tuck it underneath. So that's going to give us negative 1. And that's going to be our slope in the x direction. And now we could choose any point we want. Any point we want. Why not choose this one? Again, we could see that all of them will be it. So then we use our formula that z, we use this point, z naught is 1. Our slope in the x direction is negative 1, so we're going to have minus 1 here. X minus x naught, so x minus what is x minus 1. Plus the slope in the y direction. Slope in the y direction is negative 2, so that'll be a minus 2. And then it's going to be y minus y naught, which is 0. Okay, so then we get z equals 1 minus x, negative 1 times negative 1 is plus 1, minus 2y times 0 is that, is 0, right? And so our equation should be z, 1 plus 1 is 2, minus x minus 2y. So there's our equation for this plane. So it's, again, find the slope in the y direction, slope in the x direction. If we have 3 points, if it's a plane, there'll be one pair of the points will have the x will not change, and one pair will have the y that will not change. Okay, so now let's take a look. What if we have a table of values? As x and y are changing, we're getting our z value out here. So each row and column is linear. As we go down, that's going to be linear, and each row has to be linear the same. So all columns have the same slope. So slope in the x direction, notice as x is changing by 1, z is going down by 1. It went from 0.5 to negative 0.5. So you could calculate that slope. But the slope in the x direction that's what we've been calling m, is going to be equal to, okay, these are your z's, these are your x's, so the z's go in top, 0.5 minus negative 0.5, so I took this one, and that means we'll have 2 minus 3. So this is negative, negative is a plus, 0.5 plus 0.5 is a 1, 2 minus 3 is a negative 1. Looks like we have a slope of negative 1. So what does this have to be? Well, again, each column in the x direction is going to have a slope of negative 1. What that means is that this value is going to go down by 1. It needs to be 0.5. This value here. What's the slope in the y direction? It's going to be our n. Well, you can see as y changes, so this is actually only changing by a half, right? It went from 1.5 to 2. The z changes from 0.5 to 1.5. Okay, so that's going to be a slope of positive 1. And notice that would work here. Negative 0.5 plus 1 gives us to this. But let's just do this with what we know. So in the top we have the z's. I'm going to do 1.5 slope formula minus 0.5 in the top, which means I'll do 2 minus 1.5, right? 2 minus 1.5 in the bottom. That gives us 1 over 0.5, which is 1 over a half, which is a slope of 2, positive 2. And again, so this is only a half of a change from here to here, going up 1, going up 1. Work's going down this way. So fill in the blank and give a formula for the function. So now we have our slope in the x direction, slope in the y direction. We could choose any of the points. So whichever you want. Let's see, they're all got decimals. Why don't we take 2, 2, and 1.5? So when x is 2, y is 2, z is 1.5. It might not be the best point, but we'll take it. Okay, so again, remember our formula. We've got z equals z naught, which is 1.5, plus slope in the x direction minus 1, x times our x minus x naught, which is 2 in this case, plus the slope in the y direction, which is 2, times y minus y naught. Not y naught, not that y naught, the actual value. Right. Y naught is 2. And that's what allows us to get all of this. So we had z equals 1.5 minus x plus 2. And then we get a plus 2y minus 4. 2 times negative 2. And we can put all that together. What do we have? We have a 1.5 plus 2. That's 3.5 minus 4. 3.5 minus 4 should give us 0.5 minus x plus 2y. So that would be our equation of the plane. Okay. And you'll see I think there's about 5 or 6 questions in the homework that get you working through these. We'll take a look at functions in 3 variables next, but I'll take a short break and post this video. Thanks. Okay, to finish up chapter 12, we're going to look at functions of 3 variables, mostly just looking at some a catalog of what these 3 variable functions would look like, and then we're going to take a quick peek at what a limit looks like with 3 variables, 3 dimensions. Okay, so first of all, what we get when we have a function of 3 variables, x, y, and z, when it's equal to a particular constant, is we get these level surfaces. Okay, so we can think of this almost as a 3-dimensional contour map. And once we have the function equal to a particular value. So they give us an example here where this is a temperature from a point as we go out, and we've got some function x squared plus y squared plus z squared, which is going to give us a sphere. And this sphere here, the sphere here at where the temperature is 100 in this little inner ball would be the equation x squared plus y squared plus z squared equals 100. And that gives us like the shell, an eggshell. I guess eggs aren't spherical, but you get the point of the skin of a basketball. Okay, and as we come out, or maybe we talk about an onion because we're actually getting multiple layers, right? 200 degrees is another, is sort of an inner one, and then 300 would be out here. So each of these are functions equal to those constants. So the most outside one would be this same equation equal to 300. So we get these shells. Okay. And then, so what do the various shapes look like? We can start talking about, not solid surfaces, but just a surface area. So x squared over a squared plus y squared over b squared. If we have this formula, that's what an elliptical paraboloid looks like. Okay, so it looks like this, and this would be the equation we would use for it. We get an ellipsoid, not quite a circle, but notice if it's all equal to 1, or again, if it was equal to 2, it would just be a little bit bigger one, right? But it gives us an ellipsoid. Sometimes we can solve it for z. We're going to talk about that in a moment. If we can solve it for z, then we can think of it as really in 2 dimensions, or 2 variables defining it. If we can't solve it for z readily, then sometimes we look at it this way. We also get, notice this, changing the signs can make a difference of how things look. So a hyperboloid, or hyperboloid in 2 sheets or 1 sheet, this one's equal to -1, that one's equal to 1. You get some interesting things going on by changing various parts of the function. So a cone has this form, and notice it gives us the negative side and the positive side, cone in 2 directions. We can get a triangular plane, would have this form of an equation. And then we have our cylindrical surface, where A is the radius outward for the cylinder, and of course it's always an a squared, or just y equals ax squared. Gives us, in 3 dimensions, a parabolic cylinder. So you'll see in the homework that they'll pull up some of those formulas, so they're there for you to use. And then just we can also talk about things as being in sort of 2 variables, 3 if the case is we have a series of level surfaces, then we get a 3 variable function, the 2 variable function subtracting z. And then the graph of f itself is when g equals 0. So we can think of this. So here's a 3 variable graph, right? X squared plus y squared equals z squared, which is a sphere. And one of the family of the spheres is if this was all equal to 1. Okay, so that's 1, has a radius of 1 out. And we could go out further and further and get various level surfaces. We could also write this equation for this particular one, sort of thinking of it as in 2 variables. So we could solve it for z, get everything over there, and subtract the x squared and the y squared, take the square root, and we get a plus and minus. So it just gives us multiple ways to work with it. And then continuity is really just, it's all the things we think about from your limits and continuity in 2 dimensions This is just going to be applied to 3 dimensions. So we're going to look at things, x and y both going towards a particular point. That limit exists as long as the closer we get to L, this limit, as long as we can get the point xy close to AB. So if they're all going kind of to the same place, okay, as we get closer and closer to that point, a lot of times it's the origin, that all the values, the output values, the z values, are going to the same place. Okay, and the function f is continuous at any given point if, as we move towards that point, we have function values. So we're, in our definition of continuity, it was kind of like if you could draw, this is continuous, you can, because you don't have to lift your pencil. Discontinuity, you had to jump and then you went over here, so this would be discontinuous. This is continuous down here. And continuous. And this is just in 3 dimensions. Okay, so take a look at the homework. There's a few problems to take a look at. Most of these concepts are just going to move us forward as we get into dealing with generating these level surface areas in dealing with calculus in 3 dimensions. Okay, so that's actually the last slide. And we'll take a look at any questions that you have during class time in any of the sections 12, 3, 4, 5, 6. That's what this week is about. We could also go back to the previous week, but remember to take a look at those hints in the homework that get you started in working through them. Thanks.